And, well, first of all, you're going to want to rewrite this integral because it's improper using our limit. So we have our variable. You can do any variable. I'm just going to use n. And as n approaches infinity, integral from 1 to n. And on the same step, I'm also going to bring this x to the 2p into the numerator as a negative exponent. So x to the negative 2p. And because p is just a number, it's just a constant. It could be any number. We're just going to, we can just do the power rule, because this is essentially x to the 5, or x to the 6th. And so we can just do the power rule for integration. And don't forget, we're evaluating this from 1 to n. Alright. So, let's analyze this, as the English teachers always say. And so, this is essentially 1 over negative 2p plus 1. But we don't really care about this, at least right now, because n is approaching infinity. That's a big problem. So we have to look at wherever n is, and that's going to be our major priority. And then if infinity goes away, and it's convergent, then we can look back at our other p. But for this question, we're not looking for any specific value, but rather a range of values. I want to know what values of p will converge, and we have a bunch of greater than and less than symbols. And so we're going to look at this in the negative 2p plus 1, right? And so what we really have is we have and so with this, we have n to the negative 2p plus 1. And so as n approaches infinity, we have a negative right here as a coefficient of this p. This one doesn't matter either. We just throw this away. And so because this negative is right here, and so as n approaches infinity, infinity to any negative power is this the same as 1 over infinity to that power. So to the 2p. Where infinity is n. And so this is just non-formal math. It would be better if you did the limit and you put n down here. But this is essentially what's happening. It's 1 over infinity to the 2p. Now, infinity to any power is still infinity. And so you have 1 over infinity, which is equal to 0, right? So what we know is that as long as this exponent is negative, it's going to be convergent. And so as long as this exponent is negative, it's going to be convergent, right? So as long as the exponent of the n, the negative 2p plus 1, is negative, so less than 0, it's convergent. And so now we can just find p. Negative 2p less than negative 1. When you divide by negative 2, don't forget that this symbol, this greater than less than symbol, flips, and we get our answer that p is greater than 1/2. So as long as p is greater than 1/2, not equal to, not less than, it will be convergent. And so that'll be our answer for number 9. Okay, on to the next question, number 10. We have the integral from 0 to infinity of x squared times e to the negative x dx. Alright, let's get to it. Alright, now that we have it written out,
Of course, we're going to do a formality with the improper integral limit as our variable. I'm going to be using n approaches infinity of our integral from 0 to n of x squared e to the negative x dx.
and so what I immediately see, you might not see it, is a integration by parts. That's one of the major things this unit. And that's because I see an algebraic term, that's x squared, and a transcendental function, e to the negative x. E to any power as a variable is a transcendental. And we'll get more into that when we get to this series. And so, we can just do by parts. You can do it with the uv minus the integral of du method. Sorry, I don't really use this method very often. You can use it if you want to, though. I prefer the tabular, because it is just what I've always used. So, we have x squared, we have 2x, we have 2, we have 0.
And so this integral will be rewritten in the form where the limit is equal to limit as n approaches infinity of this integral, that integral gets rewritten as negative x squared e to the negative x minus 2x times e to the negative x minus 2 e to the negative x. And we're done.
And so now we just have to evaluate this stuff. I'll write out an evaluation from 0 to n. But look, each one of these terms has this, e to a negative power. And so if these are plugged in for n, if n is in each of these x's, that means that as n increases and goes on to, almost missed it, goes on to infinity, that these will approach 0, and 0 times anything is 0. And so this n term goes away. And so now we're just left with the negative 0 portion when you plug in 0. So plug in 0 for x right here, that's 0. 0 times anything is 0. Plug in 0 for x right here, anything is 0. But this right here is different. E to the negative 0 is just the same as e to the 0. E to the 0 is equal to 1. And then 1 times negative 2 is just negative 2. And so now you have negative 2, which is equal to positive 2, which is our answer, and that would be answer number, or letter D. There you go.
But I see a u substitution. So u equal to 1 minus 2 root x. And now when I derive, this 1 is not a coefficient to anything, so it'll just go away. And we're going to be deriving that negative 2 root x. And so the negative 2 stays over. And now we're doing the derivative of root x, which we just saw. The derivative of root x is 1 over 2 root x. And so now we would have a negative 2 times 1 over 2 root x. And obviously, these 2's are going to cancel, and we'll just be left with negative 1 over root x dx. Right, which we have a run over root x. It's this portion right here. Awesome. We just need to manufacture a negative. So we can throw a negative there, throw a negative there, and now we can do our substitution. We'll have du. It's technically multiplication, it's fine. All over u. And so now our answer is simple from here. Negative natural log, absolute value 1 minus 2 root x absolute end plus a constant, and that is our solution right there.
So for this one, try to do u sub, but unfortunately that doesn't work out because you just get 3 and you can't manufacture that x on top. What I really see, I see a by parts. And so let's try that out.
Now we do this integral. Now this is pretty simple, but I'll write it out anyways, it's alright. We'll have 2 plus 3x, and we're just going to do a u substitution. U equal to 2 plus 3x du equal to 3 dx. And so now I just have to manufacture a 3, so we'll have a 3 right here, and a 1/3 out here, right? And so this will become 1/3 the integral of 1 by the square root of u du. And now, again, we can use one of those root identities we know. And so we have 1/3 times 2 root u, and u is equal to 2 plus 3x. And so we can just immediately substitution back into this. And we'll actually at the end, no worries. So we have 2/3 square root 2 plus 3x, and that's our integral. And that's going to go into our slot here for our di method. Times. Oh, sorry, I put the 2, my bad. Root 2 plus 3x. Now let's use our by parts method. And so this integral is equal to 2/3 x root 2 plus 3x minus, sorry, I forgot this, the integral of 2/3 square root 2 plus 3x. And so, from here, it's just a basic u substitution again. It's the same u substitution we did up here. And so u will equal 2 plus 3x, du will be 3, so we'll have to manufacture a 3 on the outside and a 1/3 on the inside, 1/3 on the outside. We can pull this 2/3 out here, so we'll have minus 2/9. I drew that 9 wrong. And we'll have root u du. And from here, it's really simple. You're just going to have 2/3 x root 2 plus 3x minus 2/9 times 2/3 u to the 3 by 2. And from here, we'll just back substitute. And that is our answer. Of course, you can multiply that out, but it's really hard to use